Shall we get started? So let's see. It's a real pleasure to have Patrick Hayden from Stanford University talking to us today. So I should say Patrick is one of my favorite speakers and thinkers and people to talk to. He of course has worked extensively on quantum information, quantum computation, and on the study of black hole physics and quantum gravity. But what I find particularly nice about Patrick's work is it always provides a new twist and a new way of looking at things. So really looking forward to your talk, Patrick.
All right, well, thank you very much, Umesh, for the kind introduction. And I hope that there will be a little bit of a twist in this talk as well. There was a twist for me. We'll see if our very distinguished panelists who know much more about fault-tolerant quantum computation than I do are equally surprised. I'm just going to work on sharing my screen here. Sorry, that did not work. Can everyone see the presentation? Yeah, okay, great. All right, so the work that I'm going to tell you about today is about a very simple goal. And the question that we set for ourselves was, what is the simplest device that you could imagine that would be capable of supporting a fault-tolerant quantum memory? A qubit that you could that could live for some very significant fraction of time. I think that we might have completely failed on the marketing of this task when we wrote the paper. We called it the paper Fault-Tolerant Qubit from a Constant Number of Components, which sounds really boring, but I think that the ideas underlying all of this are quite interesting and exciting. And so the paper is joint work with Soonwon Choi and Isaac Kim, both of whom were postdocs when we did it, and they're now faculty, and Noah Shetty and Kiana Wan, who were graduate students in my group. So by now, it's quite exciting. There are multiple approaches to quantum computation that are actually significantly advanced and capable of controlling a decent number of qubits. You're all familiar with the Google Sycamore chip that was used for a quantum supremacy demonstration. Trapped ion processors have very good gate quality and coherence times. And these devices, it's worth actually observing, are quite faithful implementations of the standard approach to thinking or to defining quantum computation in the circuit model. In each of them, there are easily identified degrees of freedom inside the device, whether it's the superconducting chip or the trapped ion processor. And there are you can implement single qubit gates, and you can, in a controlled way, interact the qubits in the system with either their neighbors or qubits maybe further away in the trapped ion processor, and implement 2 qubit gates. And so these are really kind of almost very natural implementations of the circuit model. Of course, there are other ways of trying to implement quantum computation. The topological approach is one that I think many of us are excited about, even if the experiments have not yet been able to really get that off the ground, including a couple of years ago, a purported discovery of Majorana fermions that could be used to fault-tolerantly protect quantum information in hardware rather than using quantum error correcting codes. But it turned out that that paper was retracted. And so topological quantum computation implemented in hardware is still something that is a dream for the future. Now, there are other implementations that you may be, potential implementations that you may be less familiar with. here in the Bay Area, a startup company called PsiQuantum is using silicon photonics to try to implement a fault-tolerant quantum computer. And in their approach, measurement, rather than interaction, I would say, plays a starring role for reasons that are quite similar to what I'll tell you about today. And if you want to know more about it, we have a representative from PsiQuantum on the panel later, and so you can ask him about what they're doing. Amazon recently also got in the game, and about a year ago, they put out a paper describing an architecture, and they are planning to use superconducting qubits, the transmon architecture, but that superconducting qubit is not actually being used as the memory of the computer, but rather as a control device, and nanomechanical oscillators would actually be the memory registers of the computer. And they're trying to move towards a separation between control and memory, similar to what happens in the computers on our desks, where different degrees of freedom or rather different systems with different characteristics are optimized for different tasks. And so what I'm going to be telling you about today incorporates aspects of both of these approaches. We're going to be making use of a hybrid system with different kinds of qubits and exploiting their respective characteristics with the goal of reducing the manufacturing, control, and calibration requirements for quantum computing. And I don't really want to claim that the device that I'm going to tell you about is actually going to solve all the problems with quantum computing. The objective of today's talk is really more to encourage us all to remember that despite the progress that has been made, there is still a lot of room for innovation on the architecture front. And I think that there are surprises yet to be found. So in the next hour or so, my goal is going to be to explain to you why this device here, can you see my cursor? Actually, I can't see you, so. Yeah, okay, great. So why this device here, which I said constant number of components, it doesn't have many components, can support a fault-tolerant qubit. And I'll just sketch out to you schematically what the components are and how this is working. And of course, over the course of the talk, I'm going to fill in a lot of the details. And so there's one controlled qubit here, which I'll call the quantum emitter. And so it's actually a little bit more than a qubit, but you can think of it as a quantum dot or a transmon qubit. And it's coupled to a waveguide. And so it can emit photons or phonons into a waveguide. And those are then routed by these switches either into a first delay line, this purple one, or a second delay line, the red one, or they can be routed to this detector. And the detector can measure the qubit in one of a few different bases. And so that's it. That's the device. And it doesn't have many, it doesn't have many parts. It only has these, the only thing that you're really controlling in a quantum mechanical way is the emitter. You're doing quantum mechanical measurements with the detector, and then there are these switches. And so you don't have a lot of, it's not like say the superconducting model of IBM or Google, where you have, if you're going to have a fault-tolerant memory, you're actually going to be simultaneously controlling hundreds of individual physical qubits. There's just one device that you're really, this one emitter that you're going to be pulsing in an appropriate way, and this is going to make a qubit. And when I say a fault-tolerant qubit, what we're going to find is that the logical qubit lifetime, well, actually, let's just think a little bit about what we'd expect. Now, if you have a delay line, that is actually a kind of a memory, right? And you could say, well, what would I expect naively to be able to do with this? Well, if I emitted a qubit into the delay line and the qubit can survive, the decoherence time of the delay line is some number, then the qubit can survive in that delay line for the coherence time. And I'll use coherence time loosely here, incorporating losses and other forms of noise. But in fact, what we find is that the logical qubit lifetime grows exponentially with the square root of the delay line coherence time. And so marginal improvements in the quality of the delay line can lead to massive improvements in the quality of the logical qubit. And to get us there, I'm going to spend 20 minutes or so introducing cluster state quantum computation, which was invented by one of our panelists, Robert Resendorf. I'm going to explain how to use this architecture to make cluster states, and then I'm going to explain why it's actually fault tolerant. And on the face of it, I mean, those of you who know anything about fault tolerance, this is going to look like a terrible way to make a fault tolerant system, because all interactions are mediated by this one qubit. But we'll see that it actually works very well. So cluster state quantum computation. Let's just think first about what a cluster state is. So in a cluster state, there are qubits at the vertices of a graph. And so here I have a graph, a square lattice, and I have a qubit at this vertex, at this vertex, at this vertex, at this vertex, and so on. And we prepare them in the plus state, the superposition of 0 and 1, the sigma x plus eigenstate. And then we entangle nearest neighbors on the graph. And so we'll interact this top left with the one right next to it, and the top left with the one below it. And the interaction is a controlled Z. And so what it does is it applies a phase, a -1 phase, if both of the qubits are in the one state, and otherwise it does nothing. And then to actually, that's actually, at that point you're done with respect to interactions between the qubits. So you just prepare this generic resource entangled state. And then the computation is actually implemented by performing a sequence of single qubit measurements. One here, one here, one here, one here. And you just perform some sequence of single qubit measurements, and you interpret the results. And that is actually a way to perform universal quantum computation. Robert Rasendorf and his collaborator, Hans Briegel, back in 2001, proved that the 2D square lattice with this architecture was universal for quantum computation. And then about 5 years later, in collaboration with Jim Harrington in 2006, Robert showed that if you made instead a 3-dimensional cubic lattice, that would not just be universal, but fault tolerant. And of course, if you want to implement non-trivial quantum computation, at the end of the day, you need it to be fault tolerant. Now, an important observation that was made early on was that the sequence of single qubit measurements could be organized so that you performed the measurements column by column on this cluster state. And so I made this, this pink vertical line here. And I should say, if anyone wants to ask a question, you should interrupt me. I can't actually see everybody because of, okay. I'm actually seeing my presentation. So just speak up if you want to ask a question.
Yeah, I had a question, but let me.
The last person I expected to have a question.
Yeah, so let me hold back and see if there's questions from the audience. Not the case. Okay, so I had a question because you said you get by with a small number of components, and if you compare this, for example, to the IBM device, you have many components. So this emitter thing that you have there on this maybe 2 slides back or so, what is it supposed to represent? Should we think of it as one protected qubit, or what?
No, I will actually get into that in more detail later.
Okay.
So I'll defer the answer to that question. Yeah. Okay, so we can measure column by column. So we measure the first column, then the second column, third, and so on like this. And once you've realized that you can do that, then you realize that it's not actually necessary to have the entire cluster state prepared all at once. That if you just prepare the first 2 columns, then the first column at that point has interacted with all of the qubits that it will ever interact with. And so then you're free to actually measure them away. So you could prepare 2 columns and then measure the first, and then prepare the third column and measure the second column, and continue like that. And so one dimension of the lattice can be effectively constructed in time rather than space. And so that's actually an important feature of the way that cluster state quantum computation is expected to be implemented in practice. Now, how do you actually use this to perform a quantum computation? This figure is actually taken from a paper of Roberts. I'll just sketch this out to you. The first step is actually going to be to measure away a number of the qubits in the cluster. And so in this diagram, everywhere, every site with an arrow or a circle is a site in the cluster. And the first step we're going to do is we're going to measure away these these circle sites, that's measuring in the sigma z eigenbasis. And the effect of that is to eliminate qubits from the cluster. And to see why, here I have a very little cluster state. And remember that these gates are controlled z's. And I said that controlled z was applying a phase of -1 if both of the qubits are in the 1 state. It's the same thing as saying that if you look at one of the qubits and it's in the 0 state, you do nothing. And if it's in the 1 state, you apply a z gate. So let's imagine now that we measured the last qubit in the sigma z eigenbasis. So we learned whether it's a 0 or a 1. In that case, we will have learned whether this controlled z gate applied the identity or the z, right? And so if applied in the case that we measure a 0, nothing happened. In the case that we measured a 1, this gate applied a z. The controlled z applied a z. And from an entanglement perspective, these states have the same structure. And from the cluster state quantum computation perspective, the effect of having this Pauli Z applied after the fact is will just require you to change your interpretation of some of the measurement results as you go forward. But as long as you keep track, it is effectively still the cluster state. Now, so that once we've measured away a number of the qubits, we're left with a structure like the one that that Robert drew here. And you can see there's some kind of, implicitly, it looks like there's maybe some information flow running from left to right. And let's see how you can actually get quantum information to propagate through a line of this cluster state. And so imagine that we have some qubit that was part of a cluster state and maybe had participated in some quantum computation. And now we want to try to move the quantum information of that qubit to another qubit in the cluster state. The first thing to observe is that the first qubit is decohered in the sigma z eigenbasis. Why is that? Well, we applied a controlled z gate, and so if the first qubit was 0, nothing happens. If the first qubit was 1, it changes the phase of the second qubit and turns the plus into a minus. And so the second qubit records whether the first qubit was in the 0 or 1 state. And so if we measure the first qubit in a basis conjugate to z, we will not learn anything about the state on the first qubit. We will not learn anything about psi. The measurement results will be probability a half 1 and probability a half 0. And it's one of those basic facts about quantum information that measurements that reveal no information, at least in the Church of the Larger Hilbert space picture, they don't destroy any information. And so psi must survive this measurement and get propagated to the second qubit. And when you do the little calculation, the way that it gets propagated is that there's first a Hadamard gate, and then depending on the outcome of the measurement on the first qubit, there's a z or there isn't a z. And so a sequence of X measurements can act as a wire propagating quantum information to the right through the system. And so here you can see the components that I've highlighted are acting as a wire or as 3 wires propagating information from left to right. Now, if we instead chose a different basis to measure that was still conjugate to Z, but was rotated in the XY plane, so we conjugate this X operator by some rotation about the Z axis. What is the effect of that? Well, a unitary that rotates about the Z axis commutes with this controlled Z operator. And so its effect, we could actually just move this unitary UZ onto psi. And so the effect is, again, to propagate the information, but with the unitary applied to psi itself as well. And so this gives us a way to apply at least rotations about the z-axis to input states. But if you notice that there's also this Hadamard sitting there, if we perform such measurements in succession, we end up conjugating these rotations by Hadamard gates. And the effect of if we conjugate an X operator by a Hadamard, we get a Z. If we conjugate a Z by a Hadamard, we get an X. And so the effect is that we'll be able to perform rotations both around the Z-axis and around the X-axis. And thanks to Leonard Euler, we learned that we can perform arbitrary rotations by performing a sequence of 3 rotations, around Z, around X, and around Z again. And so we can perform arbitrary rotations and then arbitrary SU2 transformations this way. And so these sections of the of the sequence of measurements that I've highlighted in pink correspond to some single qubit gates, arbitrary single qubit gates being applied. And so now we've learned that we can perform arbitrary single qubit gates. And you probably remember from your studies of universal quantum computation that if you can perform every single qubit gate, then if you supplement that by any non-trivial 2-qubit gate, you get universality. And so the structures here that I've highlighted in green, by the same argument that I wrote above, the measurements aren't going to reveal anything about the incoming information. So they're going to perform some non-trivial unitary transformations on the 2 qubits. And so we have universality. And it turns out the non-trivial unitary transformation applies as a form of the controlled Z there as well. So that's it. That is basically the proof, Robert's proof, that the cluster state architecture is universal for quantum computing. And it may not be the most efficient way to make use of this resource, right? Because we're just actually translating a circuit into the cluster state architecture, but it's a demonstration that of universality, and from then you can try to optimize computations for use in this architecture. Now to get fault tolerance, again, Robert and Jim Harrington demonstrated this could be done by going to a 3-dimensional cluster state. So what is the idea there? The idea, I'm not going to draw the individual qubits here, but time is again running from left to right. And so I have a cluster state that is organized in planes. What were columns before are now planes, like this. I have the purple plane and then next to another one and so on. And we're going to encode the quantum information in each one of those planes into a planar quantum error correcting code like the toric code. And you could imagine using the circuit description or the circuit translation that I just described to you, encoding a state of the toric code and then performing the error correction as you go along, using the tools that we described before. That is actually not the most efficient, the best way to do this, that you can work more natively with the cluster state, but at least from the point of view of intuition, that can give you an idea about how you would encode and protect quantum information inside a 3-dimensional cluster state by using a 2-dimensional quantum error correcting code. So using, again, this more native description of how you would actually protect quantum information or make use of the toric code in the cluster state, Robert and Jim found that if you applied random Pauli noise, and so basically depolarizing noise, there was a surprisingly high threshold for this architecture that you could, at every time step, corrupt every qubit with probability 0.58%, and still be able to recover and perform universal quantum computation. And so this is one of the great virtues of this architecture. Noticed again, it's been known for 15 years, is that the threshold is actually remarkably high. And after their original paper, subsequent optimizations pushed the threshold up almost to 1%. Now, a little aside on fault-tolerant circuit design. Here I have a qubit then being encoded into, so my horizontal line here should be, you should think of that as a single qubit. I have a quantum state psi, and then I encode it into 7 qubits. I want this to be an error correcting code. So I'll call the encoded state psi bar. And let's suppose that the code can correct for an arbitrary error on one unknown qubit, any error happening anywhere. It's important not just to be able to encode information, but to be able to act on the physical degrees of freedom to compute. And we can ask, well, how do you compute on encoded data? Now, the first thing that might come to mind is you might say, well, let's just act on one of the physical qubits to see if we can do something non-trivial. And of course, you can't do anything non-trivial acting on a single qubit because that would be indistinguishable from the noise that the code was designed to correct against. And so that's not going to do anything non-trivial to the encoded state. So then your next idea might be, well, let's act on more than one qubit at a time. So here I have this operator W that's going to act on a pair of qubits, and that can do something non-trivial to the state potentially, the encoded state. However, if an error occurred on one of the qubits prior to the application of this W gate, if we commute the error past the gate, we'll have two errors, acting on two different qubits. And this code is not designed to protect against two errors anymore. And so we're taken outside of the realm of correctability potentially by applying this kind of gate. And so what do we do instead? We want gates that act on multiple qubits, but they act on multiple qubits independently. And so here I have 4 unitaries, each acting on a single qubit. And with this setup, if we have an error acting on a single gate, or rather on a single qubit, if we commute the error past the gate, it's still an error acting on a single qubit, and that's going to be correctable. And so this was an aside on, I just want to seed this this discussion in your minds. And the reason is going to be basically that the architecture that I'm going to propose seems to violate this rule of thumb that is often guiding our approach to designing fault-tolerant quantum circuits, which is to avoid gates that can propagate errors between physical qubits. Our architecture is going to be about as bad on that front as you could possibly imagine. All right, so how do you prepare cluster states using one of these single emitters? Well, first, Robert was asking, how he should think of this emitter. In the simplest version, we're going to, ours is a little bit more complicated than this, but there was a proposal due to Linder and Rudolph back in 2009 to prepare one-dimensional cluster states with a quantum dot. So that's what they were end-to-end waveguide. And the quantum dot was assumed to have a level structure like I've shown here. The 0 and the 1 were 2 different energy levels. And then there was another energy level, such that you could drive transitions from the 1 up to this excited state E. And then if the system was in the E state, it would rapidly decay back to the 1, emitting a pulse into the waveguide. And so if the system was in 0, you don't get a pulse in the waveguide. If the emitter was in 1, then you do get a pulse. And so inside the waveguide, a 0 corresponded to no pulse and a 1 corresponded to a pulse. And by driving transitions between 0 and 1, you can make the Hadamard gate. By driving transitions between the 1 and the excited state, you can basically perform the controlled X gate between the emitter and these waveguide qubits. And so this was a way to make a one-dimensional using an emitter and a waveguide. A few years ago, one of my co-authors, Soonwon Choi, and his co-authors, pointed out that with a relatively simple extension of this Linder-Rudolph architecture, you could make a 2-dimensional cluster state and thereby actually make it a resource universal for quantum computation. And the idea was you use the same quantum emitter, but it emitted, say, to the left, in the left direction. So it emitted one of these blue pulses into a waveguide that then bounced. The pulses would eventually bounce off a mirror, come back, interact with the emitter a second time, and then travel to the right as these red pulses, and then eventually be measured if you wanted to perform quantum computation. So why does this actually make a 2D cluster state? You could imagine a 1D cluster state. It's just a line. So you could take your line and you could wrap it in a spiral, right? Now, sending the pulses first towards the mirror and then coming back has the effect of just implementing a delay before they interact with the emitter again. And so I have this spiral of pulses now, and a blue pulse comes back to the emitter and interacts with the emitter, thereby creating the opportunity to establish entanglement with a pulse which is going to be created later, or being created at that time. And so that gives you the opportunity to create these, my spiral is on its side here, and so that links between different levels in the spiral. And so I have a picture here of Trajan's column, right? So in Trajan's column, there's a story which is happening, and it's wrapping around the column. And so there's definitely a direction of time which corresponds to this one-dimensional depiction of a scene. But the occupants of the scene at one level could actually reach up and touch the toes of the people at a time in the future, right? And that's basically what this delay in the waveguide allows you to do. it allows you to create a cluster state which is wrapped around a cylinder. And so that's a two-dimensional object, and that's going to be universal for quantum computation. And of course, the next natural step is the three-dimensional cluster state. Now, the abstract problem that we're going to have to solve, where we can strip away a lot of the complication, is just to prepare a cluster state using interactions only between this emitter, and the emitter is the object that we can control, and data qubits. And the data qubits have no two qubit gates between them. There are only 2 qubit gates. The only gates at all are on the emitter, and 2 qubit gates from the emitter to one of the data qubits. And the simplest solution for making a cluster state, subject to these constraints, is to use swap gates. So here I want to make a little triangular cluster state, and I have my emitter Q. So what could I do? I could first apply controlled Z between the emitter and the first qubit that's supposed to be part of the cluster state. And then I could swap Q into the position of the 2 qubit. And then I could apply 2 more controlled Zs, and then swap Q into the third position. And then I would have made my cluster state. Done, right? Now, the obstacle to doing that for us is going to be that we're now concerned about fault tolerance. And so we're not going to want to use exactly the same setup that Lindner and Rudolph and then Pickler and Choi were using, because we're going to want our data qubits to be dual rail. And what that means is that instead of the presence or absence of a pulse in the waveguide corresponding to a qubit, the timing of the pulse is going to correspond to the state of the qubit. And the reason for doing that is that this makes losses in the waveguide detectable. And detectable loss errors are orders of magnitude more benign than losses that when you don't know that they've happened. And so if the presence or absence of a qubit or of a pulse was your qubit, then when there's a loss, you don't know whether that was a 0 or a lost qubit. But if you use a dual rail qubit, then losses are much more benign. The price we pay for that, though, is that we don't actually have a natural way to implement the swap gate. But it turns out that a swap followed by a controlled Z, and you'll remember that we have, that's the kind of thing that we want to actually do, is equivalent to a C0 followed by a Hadamard, provided the target state, that you're applying this C0 to, is in the 0 state, and the initial state that you're going to swap with was in a plus state. So remember that the first step of preparing a cluster state was to prepare the plus. So instead, we're going to actually start off with our data qubits in the 0 and then apply controlled knots and Hadamards. All right, so let's actually just see how we'd use this setup to make a 2D cluster state before we make the 3D cluster state. So this is drawn a little bit differently than before. I have my emitter, and it's going to emit into this waveguide whose length is designed to allow L time steps. And after L time steps, the propagating qubit in the waveguide is going to come back and interact with the emitter a second time and then get measured, ultimately. All right, so the first thing we'll do is we're going to apply a C0 and then a Hadamard. So that's going to generate our first pulse. And so there's going to be a pulse in the waveguide. And remember that the C0 and then the Hadamard is the same as a swap and then a controlled Z. And so that actually just establishes an entangled state between the emitter and the first qubit. And then we're going to do the same thing. We're going to apply a C0 and another Hadamard. And let's just actually think about what that's going to do. So a C0 and then a Hadamard is going to be the same as swapping Q into the second position and then applying another controlled Z gate. So we swapped the emitter state into the second position, and the emitter had been entangled with the 1. And so we have the first link in our cluster state. And then we also have the emitter entangled with 2. And then we do it again. And now we have the third qubit of our cluster state. And qubits 1, 2, 3 are propagating through the waveguide, and 1 is about to come back to the emitter. So 1 comes back to the emitter, and when it comes back to the emitter, it interacts with the emitter and implements a controlled Z. So there's my controlled Z. And that establish this link between one and the emitter in my current quantum state, and then I apply my C0 Hadamard combination, which swaps Q into position 4. And so I've actually now started creating the second row of my cluster state, and then I just repeat this, and so on. And this way I actually make the spiraling two-dimensional cluster state. And to get to 3D cluster state, you really actually just have to do the same thing. And so I can't claim there's really any innovation here. We just took the same idea that Pickler et al. Had come up to make a 2D cluster state and added a second delay line, and the second delay line allows you to create another level. And so again, just to set things up, we have the emitter. The emitter is going to emit into the waveguide, this first waveguide, whose length is L time steps. And then it moves into it interacts with the emitter before moving into the second waveguide, whose length is L squared minus L time steps, so that it comes back to interact with the emitter a second time after a total of L squared time steps. L, the length of the first waveguide plus the length of the second waveguide. And my claim is that this is going to make the three-dimensional cluster state for you. The circuit corresponding to that sequence of interactions is drawn below. And now I'll highlight my two different waveguides are now blue and purple. And when each of the data qubits is inside one of the waveguides, I've highlighted them in the appropriate color. So the first qubit starts off propagating through the blue waveguide and then interacts with the emitter, makes a controlled Z gate, and then moves through the purple waveguide, and then interacts with the emitter again. And this is where things get interesting, because qubit 1 at this step interacts with the emitter a second time, performs a controlled Z. And when is it doing that? It's doing that right before we're about to emit a pulse into the 10th position. And the 10th position is this first qubit in the second layer of the three-dimensional cluster state. And so this controlled Z that happens when the first qubit comes out of the purple waveguide corresponds to establishing the first length into the screen, right, between the first layer of the cluster state and the second layer of the cluster state. And so you just repeat, and this is going to make the three-dimensional cluster state for you. Now, again, there's no real innovation there. And in fact, it seems like a bad idea. And the reason it seems like a bad idea is that this architecture looks like it could potentially propagate errors quite badly, because every interaction is mediated by this emitter. Every qubit interacts only with the emitter, and so errors in the emitter seem like they're going to propagate all over the circuit. And that seems to avoid this rule of thumb that we should design fault-tolerant circuits in such a way that they don't propagate errors between physical qubits. So let's see if that actually happens. Suppose that there's an X error at the step that I've just indicated here. What's going to happen? If we commute that X error past the first controlled Z, then we're going to have errors on the emitter and now on qubit 2. And we commute it past the second controlled Z, we're now going to have an error on the emitter, on qubit 2, on qubit 5. And you can look at what's going to happen, do the algebra, and this single X error, by the time you're done constructing your cluster state, is going to be a collection of errors on half of all the data qubits. And so this looks like a worst case scenario. This is like an epidemic where the doctor is contagious and she's going from house to house, infecting all of the previously healthy patients during her house calls. This really does not seem like a good way to design a fault-tolerant circuit preparation or cluster state preparation scheme. At this point, though, it's useful to step back and think about the cluster state a little bit more abstractly, not in terms of the circuit that prepares it, but instead in terms of its algebraic properties. And so the cluster state can be characterized as the unique +1 eigenstate of a set of commuting operators. So it's a stabilizer state. And if you're familiar with that language. And so for each vertex in the cluster state, there's an operator. And so say for the eighth qubit here, the operator would be to apply an X on qubit 8 and then Zs on each of the neighboring qubits. So a Z on 7, a Z on 2, a Z on 9, a Z on 11, and there might be some other ones because remember there are these periodic boundary conditions, but they're not drawn here. And so the stabilizer associated with site 8, qubit 8 is this one here, with site 10 is this one here. It's always an X on the site and then Zs on all of the neighbors. Well, because the cluster state is left invariant by these stabilizer operators, we could act on the cluster state by these operators and it's not going to affect the cluster state. And so the errors that we get that have been propagated through the whole circuit are equivalent to the multiplication of the reds in each row with the blues that I've drawn here. Each blue column, the first blue corresponds to the S8 stabilizer, the second blue column corresponds to the S10 stabilizer. And remember the Pauli operator is square to the identity. And so we actually now don't have an error on qubit 2. We don't have an error on qubit 4. We don't have an error on qubit 5. But Z cubed is an error. So we do have an error on qubit 7 and so on. And so all of those errors that we propagated through the circuit, where we actually damaged, it looked like we had damaged half of the qubits in the cluster state, they're actually equivalent to a single error, a Z error on the 7th qubit. And this seems like a small miracle, but it's actually true in general. Any single qubit circuit error, gate error, becomes an error supported in the neighborhood of a single qubit of the cluster state. And to see why, I erased an observation here, so we're going to go straight to number 2. The key point is that at every step of this cluster state preparation circuit, the quantum state is actually a cluster state. It's not necessarily the cluster state that we want, it's not our final cluster state, but it's some cluster state. And so we can use the reasoning to think about what would happen if there were the X error at this time that I indicated earlier. So the X error is on the emitter. So we'll put the X error on the emitter. And this is a cluster state. So there's a stabilizer operator associated with the emitter now, which is an X on the emitter and a Z on its neighbors. And so there's a Z on 7. And so this X error on the emitter is just equivalent to a Z error on site 7. And that's what we saw earlier, that this, what looked like a spray of errors all over the circuit is actually equivalent in this case to a single qubit error on a single data qubit. Let's look at another example. So if we had an error, again, let's say it's an X error at this site in the circuit, that is and let's say it's an error on the emitter again. The stabilizer for the emitter, is an X on the emitter and Zs on qubit 4 and qubit 7. And so we can turn this X error on the emitter into Z errors on 4 and 7. And then the next CNOT and Hadamard is going to swap the emitter into site 10. And so these errors are going to be errors on, these two Z errors are going to be Z errors in a neighborhood of site 10 in the cluster state. And so this is the essential reason that what looked like a terrible architecture for building a fault-tolerant quantum memory actually is much better than one would expect. So how well does this work? We looked at, we studied this question for a standard model of depolarizing noise. And so after every single qubit operation, a gate, a measurement, or state preparation, we have depolarizing noise with some probability. And after 2 qubit gates, we have 2 qubit depolarizing noise, again, with the same error probability. And we could find the threshold. Again, the way that you find the threshold is by noticing that above threshold, trying to perform this error correction makes things worse. Above threshold or below threshold, trying to perform the error correction makes things better. And so the point where these lines all cross is the point where the threshold is. And we find a threshold probability, error probability of 0.39%. This is a little bit worse than what Rausendorf and Harrington found. They had 0.58. but we expected it to be worse, right? Because single qubit errors, as we found, can propagate to errors on a neighborhood of a single qubit in the final cluster state. But it's not terribly worse. So we've paid a price, but it's a reasonable price. This is still quite a high threshold. And in many cases, the dominant form of noise in the waveguide is going to be loss noise. And remember, we jumped through some hoops in order to be able to make losses detectable. And so we actually calculated the threshold for combinations of losses in the waveguide and gate errors in the circuit. And you can see here, if there's no loss, so loss is 0, we have the 0.39% gate level error threshold. But if there's actually if there are no gate errors, if the gates were noiseless, then we can actually tolerate losses in the waveguide up to about 22%. And so this is why, as I said, detectable loss errors are much more benign than undetectable loss errors. You can lose a macroscopic fraction of all of the qubits in the waveguide and still be able to actually preserve your logical qubit. Now, that is not quite the end of the story, however, because remember, we are keeping our qubits in the delay line, and the delay line, the longer the delay line, the more losses the qubits are likely to incur, or rather, the more loss there is going to be. At some point, if you make your delay line too long, all of your qubits, all of your pulses are going to be lost, and there will be no quantum information to speak of. And so instead of a strict threshold, like I was describing before, what we actually get is that the logical qubit lifetime scales as exponentially in the square root of the delay line coherence time. And to see why that is, we can kind of argue it heuristically. We're using a topological code, the toric code inside the cluster state. And so logical operations in the toric code are topological, which means that to incur a logical error, you need a sequence of errors inside the toric code that look like a topologically non-trivial loop or cycle. And the probability of that happening, if the error rate is low, is exponentially small in the linear size of the toric code. This is the standard fact about topological quantum error correction, and the reason that we like it. The larger the the larger the system, the smaller the errors. Now, in our case, the delay line error probability, as I was saying, grows with the size of the delay line, and the total length of the delay line is L squared, and so the delay line error probability is eta times eta times L squared, where eta is the delay line error rate. And so we have this trade-off where increasing the linear size of the cluster state decreases the logical error probability, provided we're below threshold, but increasing the linear size of the cluster state eventually causes us to exceed the threshold and not be able to perform any useful error correction at all. And so what you would expect is that there's going to be some optimal size for your cluster state, where the total delay line error probability, eta times L squared, is about the threshold probability for the toric code. And if you just substitute in that expression for L into the logical error probability, what you find is that the logical error probability is going to scale exponentially with -1 over the delay line error rate, which is just another way of saying that the logical qubit lifetime is going to scale exponentially with the lifetime of a qubit in the delay line. So that was a heuristic argument, but we verified this experimentally. The agreement is very good. And then we can find, using what we think are realistic estimates for different parameters in the problem, well, actually, we can just find that there's a break-even point for losses. That if we just fix the gate error probability at 10 to the minus 3, so that we're below threshold for the gate errors, then we break even with a loss probability of 7.4 times 10 to the minus 4. And again, making for optical fiber, if we had a delay of 17 nanoseconds between photons, the loss rate is in the same vicinity, about 9.6 times 10 to the minus 4. So we're right around, we're not quite at the point where this would be useful if we were actually implementing this with optical fiber, but we're not so far off. And of course, optical fiber has been optimized relentlessly for commercial reasons, so we don't expect to have massive improvements in the quality of optical fiber soon. But if you could improve current technology by a factor of about 20, then you could push the logical error rate down to about 10 to the minus 10. If you improved another 2.5 times, because of the power of exponentials, you can get the logical error probability down to about 10 to the minus 15. And that's essentially the story. I guess I will just say briefly, there are many different possible architectures or physical realizations of this approach. And I think that the most likely to be viable may not actually be, say, a quantum dot coupled to optical fiber, but instead a transmon qubit coupled piezoelectrically to a nanomechanical oscillator or nanomechanical waveguide. And so we have an expert on that kind of technology on the panel, Amir Naini Safabi, and so we can get his views on how realistic it is for that to actually happen. And so what have we actually done here? The goal was to find a way of building a fault-tolerant qubit using as few components as possible, the simplest possible technology. And I think we have a proposal which is very simple. It turns out that the quality of the components is not exceeds what is currently available technologically, but because there are very few of them, at some point, once we cross these thresholds and cross the break-even point, at that point, every marginal improvement is going to lead to tremendous improvements in lifetime. And again, I'll just stress that with respect to the emitter, it is sufficient to get the emitter error rate down below threshold, like 10 to the minus 3. And then at that point, improvements only in the quality of the waveguide will lead to dramatic improvements in the lifetime of the logical qubit. We also found that despite the seemingly brain-dead design of this system that looked like it would be terrible from the point of view of fault tolerance, it nonetheless actually stores quantum information quite well. And even though it does propagate errors, it propagates errors in a way which is completely benign because of the stabilizer structure of the cluster state. And just to finally reiterate, the big point that I want to make here is that people studying fault tolerance in quantum computation for many, many years made the simplifying assumption that all of the qubits that they were going to be working with were of the same type. They had similar control characteristics and noise characteristics, and then you designed a fault-tolerant system to deal with those problems. But experimentalists taught us, and I think last week Michel Devereux spoke in this in the setting. It was actually their work that in some ways inspired me to start looking at hybrid systems. Experimentalists taught us that in realistic physical systems, you will often have access to different kinds of qubits with very different properties. And that's a lever that we can exploit. And I think it is happening these days to some extent, but I think it's really a direction that us theorists should really be pushing hard on, because we can see here that it's the ratio of timescales associated with two different kinds of qubits that actually defines the logical qubit lifetime in this setting. And so leveraging the differences between qubits can be very advantageous. And at the same time, or the other thing that I think we should be pushing on, some of the rules of thumb that we have worked by or sort of labored with in our design of fault-tolerant quantum circuits may actually be restricting us and preventing us from looking at architectures that may actually be more powerful and more effective than we thought. And on that note, I will stop. Thank you for your attention.
Great, thank you, Patrick. That was a superb talk, really beautiful. So let's see if there are any questions. I know Andrew had several questions in the chat, but maybe he can speak up himself.
Sure. I also enjoyed your talk very much, Patrick. Thank you. I did write a couple of questions in the chat. I guess you can read them at your leisure later. I will maybe just say them briefly here, though.
Okay.
First, you said that having constant components was maybe banal at the beginning, but I actually found it rather jarring, because when I think of fault tolerance, I think about doing an arbitrarily precise simulation of an ideal process using faulty components. And it sounds like you just have a constant number of components to get you an arbitrarily good simulation. And of course, it's the constant number of components, but presumably this delay line has to get longer and longer and longer. Something must have to scale. Otherwise, it doesn't make any sense. I mean, in that same notion, you could say traditional fault tolerance, all you need are qubits and a constant number of gates, and that's it. And you can do, anything. So something must have to grow to do arbitrarily good precision simulations of an ideal circuit, right? And am I right that it's really the length of the delay line that grows here, or what is it that scales, I guess, to do?
No, that's exactly right. It's the length of the delay line, and right. So yeah, so something has to scale, but it's something that you don't have to control, right? And so I treat the delay line as a single component, but the longer it is, as we found, there's an optimal length for the delay line that depends on the error, the error rate in the delay line. That if you make the delay line too long, then you're going to push, you're going to end up above threshold, and you're not going to be able to perform any error correction. And so you find the optimal length of the delay line, and then that tells you what your logical qubit lifetime is going to be.
Okay, so I would say that's not fault tolerant, but perhaps gives you a very good quality qubit, much in the way that modern transistors are not fault tolerant, but they're very, very robust to error, so we don't worry about it.
Yeah, so if you define fault tolerant as allowing you to perform arbitrarily, or to preserve the qubit memory as long as you want, then it won't be fault tolerant. But with some not terribly scary parameters, you can get logical qubit lifetimes that go like, that are 10 to the 15 circuit steps, and then for all intents and purposes, that's fault tolerant.
Okay. The other question I had is maybe more to sort of tee up a conversation between you and Daniel Latinsky, who I see is on the line here and is also a panelist, which is that the architecture that we've proposed sounds to me very similar to this so-called interleaving architecture that Quantum has proposed for their fusion-based quantum computing architecture, where they, again, are using, emitters, if you will, that are connected. And there's this L-squared story and the exponential story, and they reuse them over and over again. Of course, they're mimicking fusion-based quantum computation, which uses single and 2 qubit measurements effectively, as opposed to just creating a large cluster state and then propagating the computation with single qubit measurements. But they're very closely related models. And in fact, Isaac Kim, who you said worked on this, also worked on that one as well. So I was wondering if you could comment maybe a little bit on the similarities and differences between these two models.
I think actually that would be a good question for our panelists. I mean, my understanding is that
maybe we can postpone it to the panel and get to other questions.
Fair enough. Fair enough.
Actually, just to follow up on something, Patrick, you said, which was maybe we should be throwing out some of the rules of thumb that we had about fault tolerance. So one of the rules of thumb we used to have was sequential computation. Where you have only one active site, inherently leads to non-fault tolerant quantum computation. That you needed some sort of parallelism where you had many active sites. And I think it sounds to me like you're saying, well, if you have a very stable memory in the form of this delay line, then of course you can keep your qubits on ice, so to speak, while you go around, sort of working on, on them one at a time. Is that sort of the thinking, or what?
Yeah. I guess that, yeah, I think your interpretation is correct. Now, we were careful in the title of this paper to say fault-tolerant qubit rather than fault-tolerant quantum computer, because we've really only made one qubit, or with this toric code, you can make a small number of qubits, but because there is some maximum size for the cluster state at any given noise rate in the delay line, you're not going to be able to pack as many qubits as you would like inside that cluster state, right? That the more you pack in, the weaker the error correction properties of the cluster or of the toric code are going to be. And so we basically are going to be able to get a small number of qubits in there. And so we can only perform quantum computation on a small number of qubits. And so to turn this into an architecture, fully fledged architecture for quantum computing, I think you would actually need to connect up a number of systems that look like this. And so we've thought a little bit about that, but not too much about how you would have basically one emitter per logical qubit. And so then you would actually be requiring some level of parallelism, because you'd be working, you'd have a number of these going at once, but less parallelism than you might have expected.
Sorry, so the thing that you just said, I'm still not quite, so you have many of these logical qubits, and then how do you, is there a way to say how you would interact between them?
Oh yeah, well, so what you basically need to do is you would need to stitch together, maybe a better way to think about it is that each one of these emitters with their own delay lines can make a well, at any given time, what it actually has sitting inside its delay lines is basically one layer of the toric code in the three-dimensional cluster state. And so what you really want to do is stitch together those patches of toric code to make a larger toric code. And then inside that larger toric code, you'd puncture it in various ways to store, to have more quantum information that you could work with. And so what would need to happen is that phonons or photons, from the waveguide associated with one of the emitters would be transferred into a waveguide for another emitter, where it could then interact with that emitter in order to perform the appropriate controlled Zs to actually stitch up a larger cluster state.
Mm-hmm.
And then from there, again, the single qubit measurements allow you to do whatever you want with that larger cluster state, including fault-tolerant quantum computation.
Great. Yeah. Any other questions? Andrea, have you been monitoring the?
Yeah, there's some questions in the Q&A. So Oliver is asking, could you elaborate on the dual rail encoding system? So which modes of the data qubits represent the state, and why does this lead to detectable loss errors?
Oh, sure. So the level structure for our emitter basically has an excited state for both the 0 and the 1, instead of just an excited state for the 1. And so we at different times we would pulse the 0 and the 1. And if our emitter was in the 0 state, and we pulsed the transition that leads to the 0, the excited state for 0, then we would end up with a pulse in the waveguide at that time for the 0 state, and then we pulse for the 1 state. And if the system was in the 1 state, then we'll end up with a pulse in the waveguide for the corresponding to the 1 state. And so the qubit state in the waveguide really is just a time bin qubit. And so let's say that if the pulse arrives early, that's a 0, and if the pulse arrives late, that's a 1. But the reason the losses are detectable is that in both cases there is a pulse, and so if there's a loss and the pulse, and if one of the pulses disappears, when we go to measure, we'll notice, oh, there was no pulse, and therefore there was a loss error. So that's the point.
Thanks. So I think there's another question, but this was basically answered already. It's how you allow logical gates between multiple qubits. I think you partially answered this.
Okay.
Okay, if there aren't any more questions, then let's go on to the panel. If you can have the videos, the panelists pinned up. I think you all at this point know who the panelists are. We have a very distinguished panel who represent various aspects of this